Let me ask you something. You've got this state-of-the-art purified water system, right? We're talking high-grade stainless steel, the best UV lamps, the whole 9 yards. Everything seems perfect. But then, a few months later, your microbial counts start to creep up. And you're just left scratching your head wondering, what on earth went wrong? Well, the answer might be hiding right where you least expect it. Oftentimes, the real culprit is this incredibly sneaky and resilient enemy called biofilm. It's basically a colony of bacteria that just loves to cling to the inside of even the most pristine, polished piping, creating this constant source of contamination. And the really scary part? It can pop up and thrive in a system that you thought was flawless. But what if I told you there's an unseen guardian working for you 24/7, protecting your entire system? Well, that's exactly what we're going to get into today. We're going to explore how the simple physics of how water moves, specifically something called turbulent flow, is your single most powerful weapon in this fight for absolute water purity. So let's dive in. So here's our game plan. First, we'll uncover that hidden threat of biofilm. Then, we're going to geek out a little on the science of flow and a crucial thing called the Reynolds number. After that, we'll see how turbulence becomes your secret weapon, how you can actually control it, and finally, the big one, how to prove all of this to absolutely ace your next regulatory audit. All right, let's jump right into our first section, the hidden biofilm threat. Because you can have the most expensive, most advanced equipment in the world, but as you're about to see, if you're not managing how your water moves, you're basically rolling out the red carpet for trouble. And here's the key takeaway. The thing that trips so many people up. The problem often isn't the quality of the water you're putting into the system. Nope. It's the speed, the velocity at which it's traveling. See, if the water moves too slowly, it gives those little bacteria the perfect chance to just settle down, latch onto the pipe walls, and start building that biofilm nightmare we talked about. So, how do we fight back? Well, we have to start speaking the language of physics. And in the world of fluid dynamics, that language revolves around one critical value, the Reynolds number. This is where we stop guessing and start taking scientific control of our systems. Okay, the Reynolds number. It's basically a predictive score. It tells us, with incredible accuracy, whether our water flow is going to be smooth and orderly or chaotic and energetic. You can think of it like a tug of war inside the pipe. It's the water's momentum trying to push forward versus its own internal friction or its stickiness holding it back. Now, don't let the symbols freak you out. This formula just breaks down the factors that we can actually influence. Density and viscosity, they're mostly tied to water temperature. The pipe diameter, that's fixed once the system is built, which leaves us with V, velocity. That is our number one most important dial we can turn to control the type of flow we get. And this, right here, this is the whole ballgame. On the left, with a low Reynolds number, you get what's called laminar flow. It's smooth, it's predictable, and it is incredibly dangerous. Why? Because that slow-moving layer of water right near the pipe wall is like a quiet, cozy neighborhood for bacteria to settle down and colonize. But on the right, that's our goal, turbulent flow. It's chaotic, it's energetic, and it creates a self-cleaning environment. That is the safety zone. Now, in the pharmaceutical world, we don't just aim for barely turbulent. Oh no. While a Reynolds number over 4,000 is technically turbulent, most global guidelines and industry experts say you should be aiming for a target well over 10,000 in your main distribution loop. This gives you a really robust, consistent, and powerful protective effect. And that brings us to our secret weapon, turbulence itself. We're not just creating chaos for the fun of it. We are strategically using a powerful physical force called shear stress to constantly protect our system from the inside out. This is the magic right here. Turbulent flow creates this force called shear stress. The best way to think about it is like millions of tiny, powerful scrubbing brushes constantly scouring the inside surface of your pipes. This physical 24/7 scrubbing action makes it almost impossible for any bacteria to get a foothold and start building that biofilm. So you end up with this amazing triple whammy of benefits. First, you've got that powerful scouring action we just talked about. Second, it gives you uniform temperature. If you're heat sanitizing at 80 degrees Celsius, turbulence makes sure that the water touching the pipe wall is just as hot as the water in the center. And third, it guarantees any chemical sanitizers you use are perfectly distributed, leaving absolutely no corner untouched. Okay, so the theory is great, it makes perfect sense. But how do we actually make this happen in the real world? This next section is all about turning that science into a practical, controllable, everyday reality for your facility. So here are your control levers. Velocity is king. It's your gas pedal. Typically, we're aiming for a flow rate somewhere between 1.5 and 2.1 meters per second. Temperature also helps. Hotter water is less sticky, so it's easier to get that high Reynolds number. And of course, your pipe's surface finish is crucial to prevent bacteria from finding little places to hide. And then there's the ultimate enemy of flow. Dead legs. These things are the absolute worst. A dead leg is any section of pipe, maybe an unused branch, where water just sits and doesn't circulate. In a dead leg, the water is stagnant, your velocity is 0, your Reynolds number is 0, and it basically becomes a perfect 5-star incubator for biofilm that can then poison your entire main loop. So, how do we hunt them down and eliminate them? It all starts with good design. You have to identify every single branch point and apply the industry standard 2D or 3D rule. This just means that the length of any of those stagnant pipe sections must be no more than 2 or 3 times its own internal diameter. It keeps those stagnant zones as small as humanly possible. And now for the final and maybe most important piece of the puzzle, proving all of this. See, it's not enough to just have a great system. You have to be able to walk an auditor through it and demonstrate that it's operating correctly and is in a constant state of control. This is the million-dollar question, isn't it? The one that keeps QA managers up at night. When an auditor walks into your facility, how do you provide them with cold, hard, objective evidence that your water system is not just safe, but totally compliant? The answer is simple. Data, data, data. You need to show them your pump settings from the variable frequency drive. You need to have continuous data logs from your flow meters, proving that your velocity is staying in that sweet spot. And, crucially, have your Reynolds number calculations ready to go. This shows you're not just guessing, you are scientifically managing your fluid dynamics. And here it is, your cheat sheet for audit success. An auditor is going to want to see those velocity and temperature logs. They'll want to see your piping and instrumentation diagrams that prove you've designed out dead legs. They'll want maintenance records, and of course, that all-important validation of your Reynolds number. This documentation isn't just paperwork, it's your proof of total control. So, if you take one thing away today, let it be this. Clean water isn't just about chemistry, it's about physics. By mastering turbulent flow, you are literally turning your entire distribution system into its own active defense mechanism. And that just leaves us with one final question for you to think about. What velocity does your facility maintain, and are you absolutely confident it's keeping you in the safety zone?